Okay, first and second derivatives for extreme max and mins. Okay, so we no longer have intervals. We're talking about functions that go on forever. They're continuous. We need to find an extreme max or min, or if there is one. Okay, right? Remember, a function could go on and not have an extreme max and min, maybe only locals. When we're looking for extreme max and min, this is what needs to come true. If our critical point for our first derivative is 0, and our critical point for our second derivative gives us a 0, we need to find out if f double prime c is greater than 0, then we have an extreme min. And it needs to obviously be on both sides of that, okay? Because it needs to not be a point of inflection. Our point of inflection here on both sides. So think of it like when it's less than 0. So when x is less than 0, f double prime c has to be greater than 0. And when x is greater than 0, f double prime c needs to be greater than 0. That's for an extreme minimum. And pretty much the opposite needs to be true for the extreme maximum. Okay? Think of it like our f prime c is 0, and our f prime double c gives us a 0, or gives us a 0. If our x is less than 0, and our double prime is less than 0, and our x is less than 0, and our f double prime c, greater than 0 is still less than 0. So in other words, if it's not flipping, it doesn't have a point of inflection, then we're looking at an extreme max or min. Okay? This is important here. We're going to zoom in. So let's find our first derivative. Our first of this derivative, well, that's going to give us 4x to the power of 3. Okay. Well, to find a critical point, we just got to set it equal to 0. 4x cubed. Our critical point is x at 0. Okay, got that. We're going to plug it into our second derivative, but we need to find our second derivative. Our second derivative is going to be 12x squared. Okay. We're going to take that value of x, so f prime prime, when it's 0. And it turns out our 12 times 0 equals 0. Okay? So our critical points are the same. They're both 0 here. What we're going to have to find now is if this is a major point of inflection, or if it's concave up or down. That'll help us find if it's a local min or max. So in other words, if our critical value is when our x is equal to 0, we need to find x less than 0, x greater than 0. Well, when x is less than 0, we have a negative term. We put into our original function, f at x, which was here we go. When x was less than 0, are we going to get a positive or negative answer? Positive, right? It's an even number exponent, so we're going to end up with a positive number. So f greater than 0. Sorry, we should have checked that with the double prime. When that's 0 or greater than 0. Sorry, less than 0. Oh my gosh. Get my words all mixed up. When f double prime x is less than 0, we are going to get a positive answer. Okay, so we're concave up. And when our f double prime x is greater than 0, and remember our double prime function was 12x squared. Well, when it's greater than 0, we're still going to get a positive answer, so we're still concave up. So because we're concave up in both points, we're not a point of inflection, we're at a minimum. But remember, it's not just any minimum. Because our critical value for our first derivative, our x equals 0, also produced 0 for our second derivative, we're not talking about a local, we're talking about an extreme minimum, okay? And if I show you quickly on the grapher, let's put that function in. X to the power of 4. You'll notice we have an extreme right at 0. That's the absolute lowest point, and it just goes up from there the rest of this graph. Okay? So that's the idea we're trying to get at when we have these things fall true on a graph.